Welcome. My name is Wessel, and I'll be talking about scalable exact inference in multi-output Gaussian processes. This work is joint work with my fantastic collaborators Eric, Will, Scott, Arno, and Richard. Let's start out with an introduction and some motivation. Gaussian processes are a powerful and popular probabilistic modeling framework for nonlinear functions. When modeling only a single output f1, the central modeling choice is the kernel, prescribing the covariance between any 2 points of the function. When modeling multiple outputs, the kernel becomes matrix valued, prescribing at any 2 points in time the covariances between all pairs of outputs. Inference and learning in general multi-output Gaussian processes is prohibitively expensive, scaling cubically both in the number of points in time n and the number of outputs p. But often, these complexities can be reduced by exploiting structure in the kernel k. Consider modeling a particle moving around in the two-dimensional plane. A common way to construct multi-output GPs is to choose a fixed basis, for example, consisting of the basis vectors h1 and h2, and to explain the observations f by taking linear combinations of these basis vectors, where the coefficients associated to the basis vectors, in this case x1 and x2, vary with time. Aggregating these basis vectors into a matrix H, this can be more compactly written as follows. We're then going to model the coefficients, x1 and x2, independently with Gaussian processes, where the assumption that the coefficients are independent and have unity variance is expressed by the requirement that KTT is equal to the identity matrix. Often, the observations y are noise corrupted, which we'll model by adding some Gaussian noise to f. In this model, we'll call x the latent processes and h the basis, or mixing matrix. In practice, we'll use m basis vectors, where typically the number of basis vectors m is much less than the number of outputs p, which means that the data lives kind of in the low-dimensional pancake around the column space of h. This model can be interpreted as a generalization of factor analysis to the time series setting, and it's a very convenient model, because it captures many existing multi-output GPs from the literature. Whereas inference and learning scale cubically in the number of outputs for general multi-output GPs, for this class of models, which we'll call the instantaneous linear mixing model, or ILMM in short, inference and learning scale cubically in the number of basis vectors instead, which can be a great reduction. The goal of this presentation is to reduce this complexity even further. But to do this, we'll need to really understand why, for the ILMM, inference and learning scale cubically with the number of basis vectors instead of the number of outputs. We're going to derive our intuition from the following key result, which is based on a projection of the data. Consider an observation for the model, comprising p outputs. We're going to take this observation and project it down to m outputs, according to some transform t. We're then going to interpret this observation, and this may sound a little bit ad hoc, but we're going to interpret this projected observation directly as an observation for the latent processes. Now, if we do this, and this may seem unjustified, but if we do this, our lives are easier, because inference scales cubically in the number of outputs, and typically m is much less than p. The original observation was observed under noise sigma. If we then observe the projected observation under the projected noise sigma t, then in the paper we prove that this procedure is without loss of information. Inference remains exact. Hence, instead of performing inference directly in the high-dimensional space, which scales cubically with the number of outputs p, we can take our data matrix, project it down to m outputs, the space of the latent processes, and perform inference in the space of the latent processes instead. To get some intuition for why we can do this, consider the expression for the log probability of some data under the model, which consists of 3 terms, where the first term is equal, exactly equal, to the likelihood of the projected observations under the projected noise. Suppose that we're going to learn the basis by maximizing this log probability with respect to h. Learning h is equivalent to learning the transform t, which means that if we learn h, we're essentially learning a transform of the data. And that's really dangerous, because what the model could do is simply send all the observations to the origin and let the latent processes concentrate all their mass on the origin to essentially obtain infinitely high likelihoods. Well, it's exactly this pathological situation that the remaining 2 terms mean to prevent. The first term takes an observation, projects it down, and then attempts to reconstruct it by passing it through the bases again. It then measures how much data is lost. The first term can therefore be interpreted as a sum of squared reconstruction errors. Similarly, the second term can be interpreted as a measure of how much noise is lost by the projection. Therefore, if we're learning the basis by maximizing this log probability with respect to the basis h, then we're trying to find a projection of the data such that the projected observations fit the latent process as well, whilst trying to not discard a too large component of the data and the noise. Our key result tells us that inference in the ILMM model class comes down to conditioning the latent processes on the projected data under the projected noise. Hence, and this is the key insight, if the latent processes are independent under the prior and the projected noise is diagonal, then the latent processes remain independent upon observing data, which means that we can treat the latent processes independently, conditioning the ith latent process only on the corresponding projected observations. This essentially decouples inference into independent single output problems, which is really nice. The model class that we'll consider in this presentation are ILMMs where the basis vectors are constrained to be orthogonal. For the mixing matrix, this means that it must be a product of some orthogonal matrix U and some diagonal scaling S square root. Whereas the ILMM can kind of be interpreted as a time-varying generalization of factor analysis, the orthogonal ILMM, or OILMM in short, can kind of be interpreted as a time-varying generalization of probabilistic PCA. The key property of the OILMM model class is that the assumption of an orthogonal basis diagonalizes the projected noise, which means that we can treat the latent processes independently. In terms of the commutative diagram, this means that instead of performing inference directly in the high-dimensional space, which scales cubically with the number of outputs p, we can take our data matrix, project it down to m outputs, the space of the latent processes, and perform inference for every one of the latent processes independently. It is clear that this procedure scales linearly in the number of latent processes, or number of basis vectors. Moreover, these inference problems are just your typical single-output GPU regression problems, which means that the method is trivially compatible with off-the-shelf single-output scaling techniques. Let's make this a little bit more concrete and consider calculating the log probability of the data under the model. First, we project the data, which comes down to a simple matrix multiplication with the data matrix Y. Then, for every one of the latent processes independently, we calculate the log probability of the corresponding projected observations. Finally, to perform the reconstruction, first, we calculate some kind of regularization term, and then add everything together to construct the log probability of the data exactly, without approximation, under the model. Let's take a step back. Inference in general multi-output GPs scales cubically with the number of outputs. We then consider the class of models that fixes a basis in the output space, where inference scales cubically with the number of basis vectors instead. We then restricted these basis vectors to be orthogonal, which reduced the complexity to a linear dependence on the number of basis vectors. But the resulting model still scales cubically with the number of points in time n. However, as we previously remarked, the decoupled problems are compatible with single-output scaling techniques, which we can use to also bring down the complexity in n. For example, using a variational-inducing point method or a d-dimensional state space approximation, we obtain a linear dependence both on the number of basis vectors m and the number of points in time n. It is clear that orthogonality gives excellent computational benefits, but how restrictive is it? Call an OILMM or ILMM separable if the kernels for all the latent processes are the same. An example of such a model is the intrinsic co-regionalization model, or ICML in short, which is still widely used. Then, we can see how restrictive the assumption of orthogonality is by comparing the ILMM and the OILMM model class. In the separable case, it turns out that we don't lose anything. And even in the non-separable case, the spatial correlations are still fully general, but the correlations through time are affected. In general, an ILMM can be approximated by an OILMM if the right singular vectors of the bases are close to unit vectors. It is worthwhile to point out that separable spatiotemporal GPs are Euler-MEMs, and that the Euler-MEM gives non-separable relaxations of separable models whilst retaining efficient inference, and this, I think, is really cool. Missing data is troublesome for the Euler-MEM, because missing data breaks orthogonality of the basis H. In the paper, however, we derive a simple and effective approximation to get around this. First, we demonstrate the computational benefits of the method by computing the log marginal likelihood of some data under the Euler-MEM and the Euler-MEM. For the Euler-MEM, due to its cubic scaling, for 25 latent processes already, one such calculation takes about 10 minutes and requires over 40 gigabytes of memory. In comparison, for the Euler-MEM, due to its linear scaling, the same calculation only takes a couple seconds and requires no more than 4 gigabytes of memory. Second, we demonstrate that the assumption of orthogonality cannot be restrictive by running the Euler-MEM and the Euler-MEM on two real-world datasets and recording the posterior predictive log probability and standardized mean squared error of held-out test data. The Euler-MEM achieves the following numbers, which are equal to those of the Euler-MEM up to 2 decimal places, which demonstrates that the methods perform nearly identically on the two datasets. Moreover, both tasks require imputing some outputs from others, which demonstrates that the missing data approximation works well. In another experiment, and the last experiment that we'll consider in this presentation, we jointly model 28 climate simulators, where every climate simulator outputs predictions at 247 spatial locations at 10,000 points in time. The figure shows the outputs of the first 10 simulators. This equals about 7,000 outputs, which comes down to about 70 million observations. The goal of this experiment is to learn a covariance between simulators, by decomposing the basis into a basis over simulators and a basis over space. To estimate the covariance between simulators, we could just simply compute the empirical covariance. However, this disregards all temporal structure, and as the figure shows, all simulators account for seasonal effects, which means that all simulators will appear very correlated. To learn a more rich covariance, it is necessary to account for these temporal correlations, and this is exactly what the model will do. We're going to use 50 latent processes and a variational inducing point method to scale to 10,000 points in time. The point of this experiment is to demonstrate that the method can be used to perform a challenging task in a simple way, because the implementation of this is really straightforward. The results are as follows. Indeed, observe that the empirical correlations show that all simulators are highly correlated, as expected. In contrast, the covariances learned by the Euler-MEM are much richer and even exhibit negative correlations, the red pixels. Let's wrap up. We have used a projection of the data to accelerate inference in multi-output GPs with orthogonal bases. The proposed method scales linearly in the number of latent processes, or linearly in the number of basis vectors, is simple to implement and trivially compatible with off-the-shelf single-output scaling techniques. Moreover, the method does not sacrifice significant expressivity. Thank you for listening, and I'd be happy to answer any questions during the Q&A.